So are there any questions before we begin about anybody thought of a project to do? Some of you have talked to me. So again, I think it's important to tell you that try to keep the problem simple, even if even as simple a problem as that lap joint. That'll be complicated enough. And any problem in 3D, it will the size of that problem, number of nodes, number of elements will just go up very quickly. So try to build up, try to choose a problem so that you can study some simple sub aspect of that problem. And again, you all can collaborate with each other if you already have study groups or something. But try to do at least the smallest problem. So whatever problem you choose, pick an aspect, try to build a model, the smallest model that it should be you're completely on your own. If you want to collaborate on the more complicated, the bigger models, that's fine. You can share the results, you can share insight, discussion, but don't copy from each other, of course. Try to write your own report. Yeah.
You want to model something like a joint,
Mm-hmm.
model the bolts as well.
So if you look at the example in the Abacus manual, I think Appendix C, it has that hinge joint. So the way they modeled that, I think that example you should definitely go through. So this is very similar to your lap joint problem. So in that case, if you look, the pin, they have modeled as a rigid body. So you can just create a rigid body as a pin, and then you can study what are the stresses that it is creating towards between the holes. If you close the holes, put the holes close together, how much does the stress increase? But during all this analysis, you have to keep in mind that if you are using a linear material, if you are using small strain, then this is a linear model. So what it really means is that if you apply a force P, you get a displacement delta and some stress sigma. Then you apply 2P, you get 2 delta and 2 sigma. It's a linear model. It doesn't matter if you apply 100,000 kilonewtons or what. It's just going to give you a linear response if you are using a linear small strain, linear elastic model. So the only thing that you can gauge is qualitative measures of when, in what cases does the stress increase, what is a good configuration of holes to put, and so on, those kinds of things. If you are using a non-linear material model, or if any of the advanced capabilities in Abacus, you might have to go through the manual some more. And especially if you're associated with some research project, if you're picking a research problem, then it might be worthwhile for you to go through that exercise anyway. Okay. But yeah, don't overcomplicate the problem. If you shoot high and do a reasonable job, I think I'll definitely take that into account. But so yeah, just general advice is to keep the model simple and try to do as much as possible. All right. So today what we are going to start is the theory of structural finite elements. So what we've been doing all up till now is basically continuum solid mechanics. We build up all our equations, how to come up with equilibrium equations, what are all the deformation map and the material properties and all that stuff. So essentially what we have taken a look till now at is these kinds of problems. So let's say we have a cantilever beam very similar to your homework problems. And if you want to analyze this with continuum finite elements, then we saw that when you started to use 4 to 8 elements along the width and the depth, then you started to get a reasonable deflection, right? When you used a 4-layer element or an 8-layer element or more, then you started to get the real displacement. This displacement started to converge. So in 3-dimensional problems, if you have 4 to 8 elements here, 4 to 8 elements here, maybe 20 to 40 elements along the length, immediately your size of elements has reached your Abacus student version's limit. So the question really becomes that if it takes these many elements to model something simple as a cantilever beam, how in the world do you go about modeling something that is 800 meters tall and has maybe tens of thousands of beams and columns, right? So you can imagine if you have tens of thousands of beams of columns, uh, each beam or column is discretized with 1,000 elements. You have 100 million elements in this building now. So each 100 million elements is about, let's say, the same number of nodes. Each node has 3 degrees of freedom. So you can see that the problem size will just blow up like anything. So obviously we cannot use these continuum types of elements for structural mechanics problems. And further, actually, in this type of problem, if you have this building, you don't want to just analyze this building by itself. It's probably sitting on some soil structure, and you want to mesh the soil beneath it as well, because any structure you're going to have that type of interaction also for earthquake or for any dynamic loads. All right, so since we don't want to model this type of a building with continuum finite elements, what are our options? What do you think we should do? What can we do? Model this whole thing as one element, or the beam or column as one element? Yes. So what the idea is similar. Instead of just one element, we can model it with a line of elements, a line of beam elements. And in order to do that, what actually people did very first, long back actually, when people started to study bending problems, they saw that if you have a problem like this, a cantilever beam, and if you apply a end load, when it bends, almost the entire deformation can be captured by one line, and rest of the problem you can express in terms of the deformation of that one line. So that's a big approximation that we are making, but that will simplify, or that will reduce the problem size by a whole lot. But no matter what, these conditions or these equations have to be satisfied, no matter what. So we know for a fact that at each and every point in this building, the sum of forces gives rise to div of sigma plus b. At each, and the sum of the moments equal to 0 gives rise to that the stress tensor is symmetric. We have some boundary conditions. And if you're using linear strains, then you have this linearized strain measure and some constitutive, some material law. This could be Hooke's law, or it could be some other general nonlinear law. So how do we make sure that all these conditions are still satisfied if we use some sort of an assumption that we will try to characterize the displacement of this beam in terms of only its center line? So that's basically the motivation and sort of the basic assumption behind this beam theory. So let's take a look at how we can formulate this type of thing. So the idea here is, let's say you have this beam, and this center line right here, we are going to try to characterize the displacement of this beam in terms of the displacement of this center line. So let's say there are some loads acting all over the surface of this beam, and after deformation, maybe it goes to some place here. So let's say after deformation, it takes this configuration, okay? And what we are going to try to do here is try to define a map. So if you remember, the way we defined the map and all that was, give me a point x and where should that point go in the final deformed configuration. Okay, so this is the center line, and if you try to figure out where this point goes, let's say this is the displacement of that point, and this displacement is going to be given by W of x3. So the idea is that if you have this sort of an initial configuration, you apply some loads, each point along this centroid is going to go to a new location. Okay, and that displacement is given by the vector W, which is a function of a scalar variable. It's a vector function of a scalar variable x, where x is defined as the x3 coordinate. So essentially what we're saying is, if we have a beam along x3, if we can find what this W is, we know where each and every point of this beam goes. So if we were to write the map of any general point in this beam, so let's consider one cross section in this beam, and let's say we are considering some point in this cross section. So this point, let's say P, this point is x1, x2, x3, x, y, z. Okay, we want to find out essentially what we want to find out is the map phi. This map phi is basically x1, x2, x3, and actually maybe I should write big x1, x2, x3, but we will not talk too much about the large deformation three-dimensional beam theory. That really is a very nice geometrically exact theory, but we will restrict ourselves again to a small strain here. So the idea is that we want to define a map which defines the entire displacement of this beam. So the first thing we said is, if you give me a point, so let's say that this, okay, let's go in a stepwise way. So the map should be equal to x3 E3. Essentially what I'm saying is, this coordinate along here, let's say this point is x3, and we want to find out where does this point P go in the final configuration. So the idea is that you will take the x3 coordinate of that point, you will displace it by W. So in order to find where this point finally goes, we will add this displacement W, which is a function, which is a vector function of a scalar variable x3. And then to find out, that will take us to a location along the new centroid. So this old centroid is completely defined by the new centroid is completely defined by this displacement function W. And now if we want to find out where does this point P go, what we try to do is, we try to imagine where does this cross section, how does this cross section take a new position. So the idea again is that the fundamental assumption in beam theory, what you might have actually studied, if you have this center line, if you bend it, we assume that each and every cross section along that beam, each and every cross section is a rigid cross section. So when you think of beam theory, what picture it should bring to your mind is a beam with each and infinitely many rigid cross sections all along the length of the beam. So this is a fundamental assumption behind the beam theory, that plane sections remain plane. Not only do they remain plane, they remain rigid. The points inside the plane are they do not move with respect to each other. So the idea is that if we are considering a rigid cross section, we want to find out where does a point P go in the new configuration, it can be written as the displacement of the centroid plus this transformation. This transformation, let's say this point P is, or this point P is this small distance. This vector is small p. This is just x1, x2. And it is defined as E1 times x1, or x1 times E1 plus, let me just write it that way. So it is x1 times E1 plus x2 times E2. So the location of this point P is given by these three coordinates. This vector P, this small p, is going from the centroid of that cross section to the point in the cross section. So if you remember, we did an example on the rigid body rotation. Do you remember that R matrix, R rigid body rotation matrix that you had to find? So essentially that is a rigid body rotation tensor, and in order to find the new position of this point might have gone to some place here, not there. In the new cross section, this point might be somewhere here. So this vector is going to be lambda cross P, lambda applied to P, where lambda is the rigid body rotation of a cross section. There are infinitely many cross sections along the length of the beam, and at this particular cross section, the rotation we are seeing is given by lambda. So this is how we basically define the map. So essentially, to add the rigid body rotation, this is what we have. This completely defines the map for a beam. So if you give me a location x, y, z anywhere in this body, if you give me a location x, y, z anywhere in this body, I can find out where it went using this map. And the idea is, again, that this point P, it has an x3 coordinate. That x3 coordinate simply displaces by omega, or w. And this further inside this cross-section plane, that's a rigid vector. And when I displace this, so let's say this was my original beam, and this was the P vector in the original configuration. Since the cross-section is rigid, when I deform it, this vector is simply rotated rigidly from one cross-section to the other. Okay, and that rotation is given by this new vector will be just lambda times this old P. So this completely defines the map. And essentially, what we have done, what have we done? If you give me any point in any beam now, using this deformation, this is an assumption, we can completely characterize the motion of this beam. So we have reduced the problem from a three-dimensional problem to a one-dimensional problem. Here, the only unknowns are this W and this rotation tensor. So if we can find out where the centroid went, and if we can find out what is the rotation of individual cross sections, that's it. We don't need to find out the entire field at each and every point in this domain. Okay, so this would be valid for large rotations also, but if you are dealing with small rotations, small displacements, in that case you can approximate this term. You can write it a little bit differently. For small rotations, this term can be written as P plus theta cross P. And the idea is that this rotation tensor is basically taking some rigid body. So try to imagine that this is a long beam, and these are all these cross sections. We are going to, if this is a vector P inside the cross section, and it rotates with the cross section. We are trying to characterize the motion of this rigid body with a rotation tensor. And if the rotations are small, then we can write this lambda cross p in this form. And where, what is this theta? This theta is nothing but the rotations, the small rotations of this rigid body. So if this is x3 coming out this way, then theta 3 is this twist angle. X1 is going up here, then theta 1 is this bending. Theta 1 is bending in the x1 and x3 plane. Similarly, if you have this as x2, then this is theta 2, and this would be our regular bending, if regular bending in the x2 x3 plane. Okay, so so if we make this assumption, we can write our u, the displacement vector, in terms of this displacement w, which is a function of x only, plus theta cross p. So this is the fundamental kinematic assumption behind beam theory for small strains. And the same idea is valid for large strains also, but the math and everything gets a little more complicated there. So once again, the only unknowns here are this displacement w and this rotation theta. So what we are saying is, if we can find out w at each and every location, and the theta, which is also a function of x at each and every location, that solves the problem. Okay, so we have reduced again the field problem to two variables of a scalar function x. So you can actually verify that this boxed equation, if you write out all the individual components, that can be written out like this. So u1 is the displacement in the x1 direction, and that will be given by the one component of this w. One component of this w is whatever it goes, displaces in the one direction. And why is this term coming? This term is coming from this part, theta cross p. So essentially what we are saying is, let's consider this rotation theta 3. So theta 3 is going to be pointing along the axis. So again, this is the cross section, this is the 3 axis, and theta 3 is twist or torsion. So any point that is in this plane is going to rotate in the plane of this cross section, and that's why we have displacement in the one direction is equal to x2 times x3. Similar relationship in the two direction. If you give me a point, where does it go in the two direction? And this 3 direction is how much is the axial plus twist. So this is the axial displacement along the length of the beam, and this is the twist due to the rigid body rotation of the cross section. Okay, so this basically defines the map, and this is the fundamental kinematic assumption behind this beam theory. All right, so so if we take this assumption and plug this back into all of these equations, that will give us the governing equations for a three-dimensional beam. Okay, and that's what I have here on the next page. So what we are going to do is just take that kinematic assumption and plug it into the three-dimensional into all those equations. And in order to do that, we need to define some variables. But pretty much the procedure is exactly the same that we had before. So if you remember, when we were talking about the 2-dimension and 3-dimension equilibrium, how did we derive that div s plus b or div sigma plus b? How did we derive that equation div sigma plus b? Equilibrium of what? Right, so we went into the final deformed configuration, we picked out a small cube, we drew all the tractions on that cube, we said sum of forces is in XYZ is 0, and that gave us div sigma plus B. So the similar type of thing that we'll do for beam theory involves not a small cube, but two adjacent rigid cross sections, a small length delta x. We are going to pick out this small body from our beam, and we are going to write the equilibrium equations for this. And in order to do that, what we need to do is to define some of these quantities. But before we get there, I think one thing I need to tell you is basically that you have this rigid, two adjacent rigid cross sections separated by a length delta x. At each and every point on the face of this cross section, there is going to be some traction, right? How do I find that traction? In any three-dimensional body, if you take a cut along, if you take a plane, the plane has some normal n, right? And the traction acting on that plane is given by this Cauchy relationship, sigma applied on the normal vector. That gives you the traction that is acting at a point on this cross section. So the idea is that since these any forces that are going to be acting on the cross-sectional face, they are obtained from the stresses, so they are internal forces. So we define this new measure of stress for the beam theory. So what we call these things as resultant forces and resultant moments. Why? Because these are actually resultants or sum of all the forces that are acting on this cross section, on this face. So what we are saying is we'll go to this small point P there. The traction at that point is Tn. If we sum that over or pretty much integrate over this entire face, we will get what is the total force that is acting on that cross section, and that is your that is the force resultant or the shear or the internal sectional forces. So what we are saying is that this Q includes actually shear and axial force, because this tau, this Tn, this is attraction, it can include shear and axial forces. In beam theory, if you remember maybe from 2 dimensions, this is something that you might actually have studied long back in statics. We used to have a small section of a beam, and we write the equilibrium equations. We get dV dx is equal to the applied load, or we get dm dx is equal to minus v, those kinds of things. So essentially we are doing the exact same thing in 3 dimensions. So this is the net or the resultant force that is acting on the cross section. But we also need to make sure that the sum of the moments is 0. So we need to define this quantity, which includes bending moments and includes torsional moments. So once again, if you have a cross section and if you have some traction at a point, what is the moment that all those tractions create about this centroid? That is this P cross the force. So a moment of a force F is R cross F. In any rigid body, if you have a force acting F, this is again from statics. If this is the rigid body, you have a traction acting at this point. The R vector, that is the position vector of the force, times or cross product with P, that gives you the moment about the centroid. So if you sum up all those moments over the cross section, that gives you the total bending moment across that cross section. So those are the 2 internal resultants, and similarly you have to define what are external resultants in order to do the equilibrium of this type of a small rigid body section. So for external forces, this body could have some body forces, self weight, that is B, and it could have some tractions all over the surface. All over the surface, it could have some tractions which I am denoting by T gamma. So if we sum all of these forces up, the internal forces get summed up, and this gives you the applied section forces. which we are denoting by Q. This Q is the applied section forces on over for this body, which includes body forces and the surface traction all along the perimeter of this pillbox. Similarly, you have applied section moments. If the body force is off center, it will create a moment. So this P cross B is the moment of the body force about the centroid. Similarly, P cross T gamma, that is the moment of this applied traction about the centroid. So these are the two applied forces. Now what we have done is we have removed all of our variables that were coming from three-dimension continuum mechanics. We have replaced them with these types of measures. Q is the measure of stresses, and Q and M are equivalent stresses in beam theory. So in 3 dimensions or 2 dimensions we had sigma, here we have Q and M. So similarly, you can also come up with measures for strains and for constitutive material law. What does Hooke's law become? But if you plug in all these things into the equilibrium equation for this body, and you say sum of forces is 0, then the equation that you get is this. And this equation is very similar to what we have before. We had div of sigma plus B, that is divergence of some stress quantity plus body force is 0. This is very similar. Divergence of the resultant stresses, or d by dx. This is a regular one-dimensional derivative of the resultant stresses plus the applied force is 0. That's div S plus B in our from a 3-dimensional body. But in addition, we also have sum of moments to be 0, and that leads to this equation. This is also very similar. This is derivative of some stress measure, which is the bending moment in this case, plus the applied bending moment is equal to 0. There is this extra term that comes in because of bending and shear interaction. But essentially, this is the exact same equation. These two equations are your equilibrium equations for beams in 3 dimensions. Okay, and so what are we going to do once we have equilibrium equations to do a finite element formulation? Take the equilibrium equation, multiply it with a virtual displacement, integrate by parts, plug in our approximation, and just the rest of the machinery is very same, is very similar. So what we are going to do now is basically specialize these equations from 3 dimensions down to 2 dimensions. Basically, the idea is that if we are working in with small strain, working with small rotations, then we can decompose the problem into a planar 2-dimensional problem. We can assume that the behavior in x1, x3 is independent of the behavior in x2, x3 if the beam's principal axes are oriented along x1, x2. Okay, so this is basically what we will do for planar. Now we are going to choose this plane x1, x3, and we are going to write out what do all these equations become. So the choice is, after we make this choice, we are just renaming some variables. We are saying that if you go to a point x anywhere along the length of the beam, the axial displacement is given by u, which would be our old W3. The transverse displacement is Wx, which just gives us the displacement along x1. This should be x1. And the rotation theta, that is the rotation of one of each of these lines. So again, think of the beam as a centroidal line where all of these rigid cross sections are attached to the centroidal line. And where do all these rigid cross sections go in the final configuration is basically what we are trying to find out. So this is the theta, this theta is the rotation of this of a cross section that is of a at a distance x. Where does this cross section rotate and go? So similarly, we can also define some new variables for axial force. N is the axial force at any cross section, and now we are basically splitting the q vector that we had before. Q is the shear force, m is the bending moment at a different at some point x. So once you have decoupled your problem in two dimensions, you have x1, x3, and you have x2, x3. You are just treating those two dimensions independently. You can also define some strain measures. So U prime, does that ring a bell? U prime is the exact same displacement that we had in one dimension, axial strains in one dimension, right? We said C U prime derivative plus B is 0. Similarly here, there is a shear strain, and this is a little bit important to see what this shear strain is. So this is the centroidal axis after deformation, let's say, this dotted blue line. What would be this angle? If I know that the equation of this line is given by W x, this is the transverse displacement of the beam. Any point, you give me any point x, it displaces vertically by W. It displaces horizontally by U, but it displacement in vertical direction is W. So what would this angle be in terms of W? Or tan of that angle? Sorry? W prime. It would be this angle, since tan theta is small, tan theta is approximated by theta, and theta, this is just dW by dx. This is the slope of this line. And what is this theta? This angle is theta. And that is basically what is measuring how much has this rigid cross section rotated. So essentially, this is the difference between these two types of theories you might have heard of. One is a Bernoulli-Euler beam theory, one is a Timoshenko shear beam theory. So once again, let's say this is the cross section, or let's say this way. If this is the cross section and it deforms and goes to this place, and if the normal always remains perpendicular to the cross section, that is, which theory is that? If the normal always remains perpendicular to the cross section. That is the Bernoulli-Euler beam theory, which says that there is no shear deformation. So the way to sort of imagine what a bending problem looks like is that if these are all the pages of this book, let's say, are the rigid cross sections, a pure bending mode would be something like this, okay? And a pure shear mode would be something like this. I don't know if you can see that. If I were to shear the two planes like this, that would be a shear deformation. In this case, you can see if it is a shear deformation, the centroidal axis is pointing somewhere like this, which is not normal to this. The normal to the cross section is like this. The centroidal axis is something like this, right? So that is basically the difference between Timoshenko beam theory or shear beam theory and pure bending, Bernoulli-Euler beam theory. So if this theta is equal to, actually that's not theta. Theta is from the horizontal direction. This angle is theta. So the idea is that when theta is equal to W prime, that is, this normal vector would be pointing in the direction of the centroidal axis. That is the case where there is no shear deformation. If there is shear deformation, then there will be an independent angle theta and an independent variable W prime. And the shear angle is nothing but the difference of these two. So this angle that I had drawn before, this angle, this is the shear angle gamma. And so those are the pretty much actually, and this curvature is also there. What is the curvature? It measures how much is how much is the rotation changing as you go along the length. So there are all these different cross sections along the length of the beam. Some cross section at x displaces like this. Some cross section at x plus delta x displaces some more. What is the rate of change of this theta with respect with respect to x? That is, the derivative of theta is defined as curvature. It doesn't matter whether it's Timoshenko beam theory, shear beam theory, or Bernoulli Euler beam theory. Curvature is always rate of change of this theta. And then once you have these strain measures, all you need is some constitutive relationships, and those constitutive relationships are that axial force N is Young's modulus times area of cross section times U prime. So this is this is the exact same thing that we had before. Stress is equal to Cu prime if A is 1 or A is constant, right? Shear force is shear modulus G. This shear modulus G is the exact same thing as our mu from Hooke's law. Shear modulus times A times the shear angle gamma. Okay, so this W prime minus theta, this angle is the shear angle. If there is no shear, then the beam is then that theory is called Bernoulli Euler beam theory, and the beam is rigid to shear, which means that the only way you can calculate shear is from reactions. And finally, you have bending moment relationship. Bending moment is EI times, maybe you've seen W double prime, but it is the exact same thing as curvature. EI times curvature is M, okay? And what are the equilibrium equations now? So equilibrium equations would be, what would be the equilibrium equation for axial? All we have to do is go back to this page. This equation is the sum of forces is equal to 0 in 3 dimensions. We are saying now that we have to apply that that equation for the axial component, this component. So what that tells us is n prime plus force distribution in the axial direction, n is equal to 0, any axial forces. Similarly, in the shear force, for the shear equation, it is going to be q prime plus transverse load. This q is the same q that is acting on the transverse surface of your beam. It is the same q, this q. And the bending moment equation is m prime plus q plus distributed moment is equal to 0. These are the 3 equations that you will have for axial, shear, and bending moment for a planar, 2-dimensional beam. And maybe these equations maybe you're not familiar with, but let's see an equation that you might be familiar with. So m is given by this quantity. If I take the derivative of this equation, what do I get? The second equation, I'll just take the derivative of this equation, m double prime plus q prime plus m is equal to 0. And now I will substitute this equation, q prime is equal to minus q, into this equation. So what do I get? And I will also substitute the value for m from this constitutive relationship. So what we get is EI theta prime times double derivative plus m minus q is equal to 0. So this is again still, this is a Timoshenko beam theory, but Now, if you were to specialize it to the Bernoulli Euler beam theory, in that case, W is equal to theta. So what we are saying is that the cross section will always remain perpendicular to this centroid line. If that is true, then this angle is always going to be equal to theta. So this theta, this normal to the cross section, would be pointing in this direction. In that case, theta and W prime would be equal, and this equation would go away. W prime, this equation would go away. So if we substitute that, what we get is EI W double prime is equal to Q minus M. So this equation, does that sound familiar? Yeah. This lowercase m is the applied moment across along the length, which is usually not needed for problems that we commonly encounter. But if you have a beam that is maybe that has a micropolar material, maybe it has small little magnets at each point along the length of the beam. If you apply a magnetic field, at each point you will have a distributed moment applied. Right. We should take the derivative of this. Yeah. So basically, this is the equation for two-dimensional beam theory, and we'll first try to study. Now, this is a one-dimensional equation. The only variable here is x, and the only unknown here is w, the transverse displacement. So that complicated three-dimensional beam, right now we are studying only with a two-dimensional beam theory. If we can somehow find w, the problem is done. Okay, so we'll develop the finite element formulation for this next time, and try to see how we can apply it to frames. And all right, so see you guys Monday.